All right, so looking ahead to this week, the activities we had planned, they're just postponed. We will still do them, but we just don't want to wait a whole long or a lot of time until we can get these out of the way. This is called, it's about a organic chemist named Percy Julian, okay? And it's off of the show Nova, and I've had a questionnaire that you follow along because it details what I think is a pretty good way of describing how a lot of different organic compounds form. They talk about, for instance, what we call intermediates, which means with inorganic compound, there's a substance that you know, an intermediate is something that you would attach to that. But we can get to that at a later time. But for right now, I just want to review today for your problem quiz tomorrow, and then Wednesday, Thursday, Friday. That is the plan, okay? To the best of your knowledge, the rest of this week, is there any activities that you would be absent for that you are aware? Okay. So, with that, plan on doing that again on Wednesday, Thursday, and Friday. Then next week I decided to implement that in. I knew I said this week was going to be a pretty big week, but I thought this was worth our time to spend time and watch that. So, and I think you'll find it beneficial as well. Okay, so this chapter, okay, deals with not just acids, not just alcohols, in the process where them two react, okay, is called what? It was the activity that you had done last week. You have an acid, an alcohol, and with a strong catalyst at the right temperatures, that process that starts with an E, esterification. That's right. And then that's just the process of forming what we consider or call a complex ester. And is it possible to reverse that reaction? Yes, it is. And would we possibly know what that is? The reason I ask is I have some gold-colored papers that would say to the contrary that, yes, we do know how to do that. And what's the opposite of esterification? Do we know what the terminology is? Yeah, it's hydrolysis, okay? And then there is one more, saponification, okay? That's correct. Those are our three. Now, saponification, is that maybe the easiest of all of them, or maybe that's the hardest to recall? Okay? So with that, my question is, how much of time do you need to go over some of this content, or are we just fine? Because this is naming and reactions tomorrow.
I think we could review a little bit.
You can review a little bit? Okay. One of each reaction. Oh, man, we're even being specific. You want to go in alphabetical order? So you do care. You got to say, I could not care less. Then you don't. It doesn't matter. Okay. So alphabetical order. Which one's first? No. Yeah, it really doesn't matter. We'll just we'll start with saponification first, not because of alphabetical order, because that's what you're introduced to first. Okay. So when it comes to saponification, okay, we need to have an acid. Okay. So give me an example of an acid. No, an organic. Sorry. Okay? We use 3 carbon compounds a lot. Is that why we chose that? I mean, that's fine. Okay? So, okay, of course, the prefix PRO means 3. Okay? And then I almost put the double bond there, which you could, okay? Because in this case, there is our propanoic acid. And then in order to perform that process of saponification means you're adding what to this acid? Not an alcohol. Because then it would be an ester. Then it would be esterification. But we want saponification. And it was on your paper that said list 2 ways. Okay? Sodium, yep, something to do with it. Okay? That just all mumbled together. So I thought I heard sodium hydroxide. Okay, all right. Okay, and we want you to be able to describe what it is that's actually happening here. And if my memory recalls or is correct, I don't believe there is a catalyst. I think this just takes place. I could be incorrect, but I want to be sure. Sodium bicarbonate? I'll get back to you. Yeah, I was correct. You don't need a catalyst for this, okay? But you need a strong base, and like you had alluded to, okay, this one is also a strong base, okay? That one could be used because a lot of you put that down on your paper, okay, which would be correct. And then what denotes a strong base? Well, a type of hydroxide compound, okay? We've got sodium hydroxide, you could have calcium hydroxide, magnesium hydroxide. Is there any problem when you're possibly using one of the alkaline earth metals? And it's not for the reason that you would think. It's maybe just a little more complex because how many hydroxide ions do we have here now? Okay, if we're starting to use some of these alkaline earth metals, this is where it gets to be maybe a little more of a problem. So technically that's right, but it's a lot more difficult if you do it that way. So what could possibly be an example of a strong base? Well, we know that sodium hydroxide is a strong base. So what's a close neighbor to it? No. Okay, lithium would possibly work, and also potassium. Potassium hydroxide would be a strong base too. Okay? And what we want you to be able to illustrate here, okay, and it's very similar to that of the alcohols in esterification. Okay? It's similar, but it's not the same. Because in esterification, this whole thing comes off. That's not the case in saponification. Okay? So this comes off, and then what's going to happen to this compound? Okay, this is actually going to attach to there, so it's kind of like replacing it, and then this comes off. So there is your water, and then here is your soap then. And then if you write plus H2O, fine. If not, we're not going to get too bent out of shape about that. Yes, we want you to illustrate it because up to this point, when I'd have like a handful of markers here. So if you just have one color and that's your pencil, we want you to know how to illustrate this process correctly. Okay. All right. Are we good with that? All right. So an acid, a strong base, and be able to illustrate that. And gives you your, could say, a type of soap that you could actually use. And I don't know how good it would be. It's just something that has to work like a detergent, breaks apart grease, then the water with, and one of the things that we talked about with the water, why does this work with water now? Because how is this bonded? Here it's covalent. On this side, it's what? It's ionic on this side. And that's why that actually works as a cleaning agent. Okay. So next would be, okay. Let's say this is what we want to create, and that is, we'll go, we'll keep them both at 5. Okay. So notice when you said pick 3, we know, okay, propanoic acid. Okay. So once we see this, we know we've got COOH. So there's our acid structure. This, on the other hand, is a different type of compound, and that is a what? That is an ester. Okay. And what makes it possibly more difficult to discern or figure out is because it's starting naming it with a derivative. So this is what we're trying to make. Okay. So how do we draw that ester? What's the structure of this ester? We said both of them are 5. Okay, so with an acid and alcohol. So is this the alcohol side or the acid side? It is. And one of the ways we know that, okay, maybe just repetition could be one, but notice that your acid ends in OIC, your esters end in ATE. So that OIC got changed to ATE, so you know that this is going to be your acid side, your alcohol side comes first, okay? So again, this is what we're making. Okay, so there is our 5-carbon derivative there. Okay, so how do we attach the acid on here now? What bonded oxygen? Okay. And then what comes after this single bonded oxygen now? 5 more carbons. Okay. Okay. And are we missing anything yet? Okay. So we could take that really, really literal and say 2, 4 on the left and say, oh, that still works though. But you didn't know that at the time. Because if we were to say 2, 3 and say, well, it's over there on the left, okay, would that be correct? No, it doesn't. Remember, we got to find the center and work outwards, okay? So 2 comma 4, and again, it's just a coincidence. It does not matter. Okay, now what are we missing on our acid side? Double bonded oxygen. Way out here? Of course not. Right there. Just kind of running out of space here because I know it's going to take some space up here. So we think it's worth our time reviewing the naming on how to write the structure of that ester out. Okay? So how do we get to that point now? Okay, so we need 2 5-carbon compounds. Okay. Does the different colored markers help you or not? You won't have them tomorrow. But does it help you today? Okay. All right. So then, which one of these do you want to be your alcohol? The left or the right? It makes more sense to put it on the left. Okay. Okay. And then it would make the most sense to put that here. Again, we're kind of running short on space. Okay. Oh, yep. Okay. You said nope?
2,4.
Oh, sure that's not 2,4? That's 2,3, isn't it? Ah. Okay. All right. Now, who gets the box here? Just the H. Okay. Now, that must mean all of this comes off then, right? Okay, so that bond is still there. That bond is still there. So this oxygen is now connecting to there. This oxygen is right there. The tricky part about this is, okay, how is that different than saponification? We said it's similar, okay? Look at what happens to our OH group with esterification, okay? That comes off, right, of the acid. Saponification, on the other hand, is just the hydrogen, okay? So they're similar, okay? Is this difficult and challenging? Yes. Are you capable? Yes. We all know that, okay? And is this easy? Of course, no. Of course not, okay? But you're all here every step of the way. So, charge, okay? So that is now correct, okay? So our pentyl 2,4 dichloropentanoate. That's how that would be produced. Okay. You have to let me know if this is not detailed enough, it's plenty detail, going too fast.
Yeah, good.
We're good? All right. So then the last portion would be is if we were going to take an ester and break it apart. Okay. So can I erase this?
Yeah.
Okay. Okay. So I think. All right. We'll make this one a little more simpler. Okay? So now I want you to name this first. We did the old switcheroo on this. Okay? What do we mean by the old switcheroo? Because we know what gets named first, the alcohol or the acid side. It's still the alcohol. When we had our other example, okay, we had the old switcheroo. The alcohol side was actually over here. So there's no derivatives hanging off of here. So what is this ester called then? Okay, so it's an ethyl group. Okay, now if there was a derivative hanging off of there, okay, we could say, okay, that wouldn't make any sense. They should probably be a little longer than that. Okay, if there was, okay, then you would start that with ethyl to what? To methyl. Okay, so we'll still keep this simple. So ethyl, and then what's our acid side called? Butanoate. Okay, so we got ethyl butanoate. Okay, so now, to me it just makes more sense to write it like that. Okay, so now you're not really using boxes because you're not breaking anything apart. You're just reassembling it to its original parts. Okay, so what do we get on this side then? Okay, so our acid is called what then? Oh boy. That's awful, isn't it? Okay, so how do we finish this? Okay, and then what's left over? Okay, so then this also breaks that apart, and there we go. So this reaction is called what? Starts with an H. That's hydrolysis. Okay, those are your three types. Okay, saponification's up here. The one prior to this one was esterification, and then this is called hydrolysis. All right. Okay, so front row. Good. Second row. We're good. All right. So as far as I'm concerned, the rest of the time then is yours. So we'll catch up to you next time.